Yeah, so that's correct. The purpose of a feature function is to indicate which y values have higher probability. And if some y values intrinsically have higher probability, then you can model that with a feature function that doesn't depend on x. But if you have a feature function that only depends on x, what would actually happen is that mathematically it would cancel from the numerator and the denominator, because you'd have some fj of x, you'd have a corresponding wj. So for every different y here, you would have the same contribution up here. And so you could divide through, so that contribution, you could cancel it from the numerator and the denominator, and it wouldn't have any influence on the relative probabilities of the different y's. Okay. Let me ask another question. So the fj set, so it's fj for j equals 1 to j equals d. So if I want to talk about the dimensionality of the problem here, the dimensionality is the number of feature functions. And d is fixed. But often the length of x and the length of y is not fixed. If x is words and y is where you can put a hyphen, or x is sentences and y is parts of speech. And so one of the machine learning issues that feature functions resolve is how to apply supervised learning to objects that don't have a fixed length or a fixed size. Because you can have a fixed number of feature functions even if the length of the x's and the y's is not fixed. But we can have, so then we can have a special constraint on each fj, and then that's what I wrote up here. So fj of xy is the sum over the length of x of little fj and then two neighboring values in the label sequence, and then the input x bar, and then the position I. Okay.
But that essentially would be unchanged if you say expand the length by 1.
Oh, it would be essentially unchanged if I expand the length by 1. So in fact, maybe something that's closer to what I would actually do in practice, and maybe sum from I equals 0 to n plus 1, where n is the length of x bar, of fj of, actually, so I equals 1 to n plus 1, fj of yi minus 1, yi, x bar I, where I define y0 is start and yn plus 1 is end. And so for so when I'm thinking about trying to predict the output sequence y, it can be computationally convenient to to just say, well, y0 is always start and yn plus 1 is always end, and then what I want to predict is whatever comes in between. Okay. So the big restriction here, so the significant restriction is that each fj can only examine two adjacent tags yi minus 1 and yi. And so I have the terminology I'm going to use is a high-level feature function fj, and then is a sum over the sequences x bar, y bar of the low-level feature function little fj. And these low-level feature functions are often more intuitive. When you're talking about sequences, the low-level feature functions can be more intuitive than the high-level feature functions. So I might have, for example, f28 of yi minus 1 yi x bar I would be that yi minus 1 yi equals 0, 0, and xi minus 1 xi equals th. So if my task was hyphenation and I had this as a low-level feature function, so the two consecutive tags are 0, 0. Remember, 0 means no hyphen, and the two corresponding consecutive letters are th. So certainly this is an instance of this type of feature function, and it satisfies the restriction that I'm only referring to two consecutive tags. So what's this? And supposing that this was my low-level feature function, and then this was my corresponding high-level feature function, and that this feature function had a positive weight, what would that be saying? Yeah?
When you have a th, you don't usually hyphenate.
Yeah, that when you have a th, you don't usually hyphenate. Yeah, I guess, yeah. You just have to choose a convention. Does 0 mean hyphen not allowed before this letter, or does 0 mean hyphen not allowed after this letter? But if my convention is that the tag refers to the hyphen after the letter, then 0, 0 means no hyphen after the t, no hyphen after the h, and most English words that contain a th, they don't have a hyphen after the t or after the h. So this is a feature function that you expect your training will give you a positive weight for the corresponding feature function big F. And you see, this is an indicator function. This low-level feature function is a 0, 1 function. But when I sum it up over the whole input, then it becomes real valued. Okay. Yes?
Well, it still bothers me that you can't look ahead on the next label.
You can. The only restriction is that you can't look at more than 2 labels at a time. But I could, for example, say xi minus 2, xi minus 1 equals equals th, and yeah. So
Stand much both ahead of yourself and behind yourself to determine your label. You only can look one direction at a time.
no, you can actually look because you can look at all of x, and you can look at two y's. So you could look at so you can look at anywhere in x. What you can't do is look at more than 2 tags at a time. So if you think back to the example of multi-label, using a log linear model for multi-label, the corresponding limitation would be that you can look at anything to do with a document, but you can't look at correlations between more than 2 labels. And here we can't look at, well, and here's an example of something that would not be allowed. F29 of y bar x bar equals yi minus 2, yi minus 1, yi equals 0, 1, 0, and xi minus 2. Okay, yeah. So this fits into the definition of a feature function in general, and it's saying, it's looking at how many 0, 1, 0 sequences are there. But it's referring to more than 2 y's, and so it's not fitting into this restriction. So, but here's a low-level feature function that would be very useful. Just yi minus 1 yi equals 1, 1. What would this feature function be useful for?
Well, basically, you're learning that you're not going to have 2 hyphens in a row.
Yes. You'll learn that this feature function has got a big negative weight, and what that means is that you don't have 2 hyphens in a row. But you won't be able to learn any patterns about 3 hyphens or non-hyphens in a row.
But if you're doing part of speech labeling, it might make a lot of sense if you have a proper noun word before me and proper noun word after me, then I'm probably proper noun word as well.
Yes. So for part of speech labeling, it would be quite useful to have low-level feature functions like proper noun, proper noun, proper noun. And that's unfortunately not allowed by this framework.
That's not allowed by CRFs or by linear CRFs?
It's not allowed by standard. It's not allowed by standard linear chain CRFs, and the reason it's not allowed is because there don't exist algorithms for that case. It's allowed theoretically, it's allowed mathematically, but then the standard algorithms will break down.
So you essentially need a multi-scale sort of models.
So if you really wanted to, if it was really important to you to have patterns like proper noun, proper noun, proper noun, you could try developing your own algorithms. You could try creating some sort of multi-scale model so that you could group words into groups and then have a CRF that referred to just pairs of consecutive groups of words, actually both of those have been tried. There are papers in the literature about both those approaches. You can relax this assumption of 2 neighboring ones, and in fact, actually So tomorrow I'm going to be presenting a paper at the conference, which is about an extension of conditional random fields. And we actually have a comparison in there to a method that was actually published by Zubin Garamani, who's professor at Cambridge University, where they have an extension of linear chain conditional random fields to allow for triples. And on this particular application, it's the best performing method because there really is a lot of information in the triples. But the algorithms for that case are much less tractable.
So the significant complexity going from pairs to triples.
The significant, well, and I think there would be additional complexity going from triples to quadruples. I think essentially the algorithms are exponential in the number of adjacent labels that you allow. So actually, linear if you don't pay attention, if you don't allow pairs of labels, and quadratic if you allow pairs of labels, cubic if you allow triples of labels.
So you could have a generalized algorithm.
Yeah, that's what I was just wondering as I was just saying that. I'm not sure if if there's a paper in the literature that explicitly gives a generalized algorithm for any fixed number of adjacent ones, because this work that I'm thinking of by Zubin Garamani, it may be, it's more general than just linear chain CRFs, because it also applies to nonlinear CRFs. And so I think there may be a gap in the literature that somebody should write a paper that that gives the algorithms that are just for linear chain CRFs, but for any number of adjacent labels. I think that might be worth doing.
Another question is adjacency that important, or is it just the fact that there are two? So if I can say why I one, why I two.
Okay. I think that, so the standard algorithms require adjacency. I think there might be non-standard algorithms that actually have the same time complexity that don't require adjacency, but the standard algorithms require adjacency. And I guess that's what I should get to next. And I thought, we have another break coming up. Do we?
Yeah,
Yeah. Sorry?
4 minutes.
In 4 minutes, yeah. So let me move on to talking about what are the two central problems that I'm going to provide algorithms for solving. So probability of y bar given x bar and w is, there's a z of x bar w, and on the numerator, exponential of sum over j, wj fj of x bar y. So to make a prediction, so y hat is the argmax over y of exp of sum over j wj fj of x bar y. So if we want to use one of these models to predict a y, then we're going to plug in the x and look for the y that has highest probability. And the y that has highest probability is the y that has the biggest value for the numerator. The denominator is constant for all y. So when we want to find the argmax of the probability, we just need to know the argmax of the numerator. And in fact, there's one more simplification that I can make on this argmax. Okay? What can I simplify? I don't actually need to find the argmax of this. I can find the argmax of something a little bit simpler.
You don't need the exponent.
I don't need the exponent because it's a monotonic function. So I need to make a prediction. I need to find the argmax over y of this sum. And what's fundamentally difficult here is that the obvious way of finding the argmax would involve enumerating over all possible y. And y comes from a discrete set. So in principle, I could enumerate over all possible y. But the number of different y is exponential, so it's going to be, in practice, intractable to enumerate over all possible y. So this is one problem I need to solve. The other problem is to evaluate probabilities, the probability of y. I must need to compute z of x bar w is the sum over all y prime of exp sum over j wj fj of x bar y. So notice that, so this is the normalization constant that makes these probabilities add up to 1. And if I want to find out what has the highest probability, I don't actually need to evaluate this normalization constant. I can just ignore it. But if I want to find out a true probability, then I do need to evaluate the normalization constant. And the intuitive difficulty in evaluating the normalization constant is the same that involves enumerating explicitly over all y. And so I'm going to provide algorithms for solving these two problems, and then I'm going to provide a training algorithm for conditional random fields, which is stochastic gradient descent, and that's going to be, those are the three basic algorithms for conditional random fields. So the algorithm for these two problems, it's, well, there's no similar algorithm for logistic regression because you don't have a similar problem. But the algorithm for training is similar to the algorithm for logistic regression because it's also a stochastic gradient method. And okay. So let's come back in when? 5:30? And we'll be refreshed. I'll be refreshed, and I'll give these algorithms. Get started on the algorithms. So we want to calculate y hat is argmax over y of sum over j wj fj x bar y bar. So this is, and we want to do this in polynomial time. It's actually going to be, I think, quadratic in the length of y. No, actually, well, linear in the length of y and quadratic in something else. So this is, now I'm going to expand the definition of the high-level feature function. Sum over j, wj, and then sum over I, little fj of yi minus 1, yi x bar I. Notice the, just so nobody's confused, so here j is ranging over the feature functions, and then I is ranging over the length of x and y. So this is for a single test example x. I is not ranging over multiple training examples, it's ranging over the length of one example. And let me, okay, so what I'm going to do is just switch the order of these summations. So argmax over y bar, sum over I, and then what I have is sum over j wj little fj yi minus 1 yi x bar I. And then I'm going to call this my g function. And I'm going to call this gi of yi minus 1 yi. So there are, in going from here to here, so this function is a function of yi minus 1 and yi. And so I still have those arguments, yi minus 1, yi. But this argument I, I'm just making it into a subscript, so I have a different g function for each I. And then x bar and w, I'm now leaving out of this notation because this argmax here that I'm interested in, it's for a specific x bar and it's for a specific w vector. And so I can leave it out of the notation.
Charles, I have
Yeah.
a feedback form here.
Okay, I guess that was it.
Participants. So, you would mind taking 2 minutes to fill out the feedback forms? We're trying to improve the tutorial program for CIK in 2009 and return the forms to the help desk over here.
Yeah. Okay. So this GI function, if you look back up here, then the thing that we want to maximize is a sum over all feature functions, all high-level feature functions, and then each high-level feature function is a sum over positions in the sequence. So now what we've said is we have a sum over positions in the sequence, and then this G function is really the total contribution from a single position I in the sequence. And and notice that yi minus 1 and yi, they belong to the set of tags. And so if I have a hyphenation problem, then there are just 2 possible tags, 0 and 1. And if I have a part of speech problem, then maybe there are 20 possible tags, 20 possible parts of speech. And x bar and w bar are fixed. So this function gi, so remember I'm trying to derive an algorithm, so algorithms depend on data structures. So what data structure can I use? What's the simple data structure that I can use to represent the function gi? Data structure for gi. So set of tags, maybe I'll call this set T with cardinality T equal M. So M is the number of different tags, 2 for hyphenation, 20 for part of speech. And I have a function gi, and I'm going to need to evaluate it for every possible combination of values yi minus 1 yi. And then I'm going to need to store this function. So what data structure could I use to store this function in? A hash? Oh, actually, I can use something even simpler. I can just use a 2-dimensional matrix because there are just 2 different arguments, and there are m values for each argument, so there are m squared possible values. Each gi is an m by m matrix. And so actually the first thing that I'm going to do in my algorithm is pre-compute these gi functions. And so literally x bar is fixed, and then for I equals 1, I just compute this sum over j, wj, little fj of yi minus 1 yi for every possible pair of values yi. So each gi is an m by m matrix.
Because of the adjacency condition that is required, you only need the m by 2.
I,
Oh, no, only for y.
yeah, so G1 is an m by m matrix, G2 is an m by m matrix, G3 is an m by m matrix. So then pre-compute all of these. So that's actually, it's m squared n times the m squared n d time. So there are n of these matrices. Each one has got m squared entries. And each entry in the matrix is a sum over d little feature functions. So it's quadratic in m, but linear otherwise. Okay. And unfortunately, I don't have much room on the board. So, and now I'll have a definition. The score of k is, score of y1 up to yk is the sum from, I guess, I equals 1 to k of gi yi minus 1 yi. So for any particular sequence of tags, y1 through yk, which is starting at the beginning of the input sequence, but not going all the way to the end of the input sequence, I can talk about the score of that sequence of tags. And then my goal is to find the best sequence of tags. So find the tag sequence with best score. The sequence y1 through yn with max score. And so define u of k is score of the best sequence y1 through yk. And then I'm going to define u of k comma v is the score of best sequence y1 through yk with yk equals v. And so this UKV is just a special case of UK where I'm adding the constraint on the last tag. And my goal is to find u of n plus 1 and then end. So I'm going to, I mentioned this before, for convenience I'm going to extend my set of tags to include two special tags called start and end, and then I'm going to just assert that the 0 tag y0 is start and the n plus 1 tag yn plus 1 is end. So now my goal is to find the score of the best sequence of tags that goes up to tag n plus 1, where tag n plus 1 equals end. So up until here, I've just redefined, just got different notation for the goal of the algorithm. Because remember, the goal is to find the argmax over all sequences of tags.
So the way you define it naturally leads you to think of a greedy type of algorithm where you find the first subsequence
Yes.
first. But can you be guaranteed that that's going to be best?
Well, yeah, good question. So yes, the way I've set it up, it leads me to think, well, can I find U1, then U2, then U3? And the answer is that I can do that in a guaranteed way by using an idea called dynamic programming. So U of kv is the max over y1 to yk minus 1 of sum from I equals 1 k minus 1 gi of yi minus 1 yi plus then gk of yi, whatever yi is, and then v, which is fixed because v is the argument of ukv. And so now comes the interesting part. I'm going to have a recurrence. So u of kv is the max over yk minus 1 of u k minus 1 comma yk minus 1 plus gk of yk minus 1 and v. So here, so let me just go back here and write this correctly. So here's the definition of UKV. It's the score of the best sequence y1 to yk with yk equals v. So it's actually a maximum over y1 to yk minus 1 of the sum of the g functions for I equals 1 up to k minus 1, and then plus the g function for y of k minus 1 and v. So this is the definition of the UKV function. But with this definition of the UKV function, I can write down a recursive way to evaluate UKV. So it's the max here over y1 to yk minus 1. So I get a free, it's the maximum over y1 to yk minus 2, and then ending in yk minus 1. But yeah. So here I have gk of yk minus 1v, that's the same. So this goes to here. And then this, so I have a free choice of yk minus 1. That's the maximum over yk minus 1. But then u of k minus 1, yk minus 1, by definition, that's the maximum over y1 to yk minus 1, or over the maximum of y1 over y1 to y of k minus 2, and then ending at yk minus 1. So this equation, this is a recursive equation that has the same meaning as this non-recursive equation. And then, so what's the advantage of the recursive equation? It's more complicated than the non-recursive equation, so what's the advantage? Yeah, so this is a dynamic programming equation now I can actually evaluate this in a loop. So I I evaluate U1 of V for all V. Then I evaluate U2 of W for all W. Then I evaluate U3 of Z for all Z, and so on. And this base case here, U1, so U of 1 comma V is the max over so it's actually yeah, so this goes like this. I'm trying to think, is the base case for U1 or U2 or as I put in the notes, I put the base case is an exercise for the reader. So what we have is that Y0 equals start. And then Y1 is, so if we have K equals 1, then, well, let me just write out the definition and it's going to work. So U of 1V is the max over Y0 of U of 0 Y0 plus G1 of Y0 V. And Y0 is constrained to be start. And U0 of Y0, we can start at 0. So this is the max over okay, yeah, it's just G of start and V. So there's no actual maximization to do for U1 because remember there's a different U1 value for each different V value, and there are M different V values. So for U1V, it's just G of start V, and that would be G1 of start V.
But this maximization includes only sequence of length 1, so we just pick the maximum.
Well, it's a maximum over. Yeah, okay, it's a trivial case because there's only one possible Y0. Yeah, yeah. And then for so U2 of V is non-trivial. So U2, so U of 2 comma V is max over Y1 of U of 1 comma Y1 plus G2 of Y1 V. So again, for every possible value of V, I have to do a maximization over Y1. And but this u1 of y1, I look it up because I calculated the previous stage. So so the time needed here is, so what is the time required to calculate u2v?
That's the number.
Linear in the number of v.
It's linear in the number of different v's, and there are m different v's. And then for each of these maximization, it's also linear in the number of v's, because for each v, I have to consider all y's. So requires order m squared time for all v. And I need to do this up until un. So finally, I compute, I guess, u of n plus 1 and end, and that gives me the argmax answer that I want. And so total time order n times m squared, because I have to go up to un plus 1. And and the time for calculating the G matrices, I think I said, for G matrices, it was order n m squared d. So this is going to dominate this, but both of them are polynomial. And this d, this is the worst case, because for for any position I in the sequence, the great majority of feature functions are going to not apply. And so if I can organize my feature functions so that I don't have to explicitly add in the zero contributions from those feature functions, I can reduce this constant. You see, it's an expensive operation, but it's polynomial. It's proportional to the length of the sequence. It's proportional to some constant, which describes how much information you have about sequence. And then it's quadratic in the number of alternative tags. So if there were 20 parts of speech, that would be 20 squared is 400. It takes a significant amount of compute time, but it's tractable because it's polynomial, and low order polynomial. Okay. And this algorithm is a special case of dynamic programming. And it's sometimes called the Viterbi algorithm. Has anybody who's seen the Viterbi algorithm before? Okay, yeah. So the Viterbi algorithm is used really for decoding hidden Markov models, and it turns out that there's conditional random fields are closely related to hidden Markov models, and it's not a surprise that this algorithm is very similar to the algorithm for finding the maximum probability sequence of states through a hidden Markov model. So it's a dynamic programming algorithm. Some people call it the Viterbi algorithm, which is the dynamic programming algorithm for finding, for using a hidden Markov model to make predictions or do recognition. And I think it's really just a question of taste whether you call this algorithm the Viterbi algorithm or just say it's in the same family. Anybody know who Viterbi algorithm is named after? And who's Viterbi? Yeah?
He developed the
Yeah,
Right, and now he's somewhere in Southern California.
yeah. So actually, we care about him in San Diego because he's in San Diego. He was a professor at UCSD for many years, and then he was the co-founder of Qualcomm, which is the company that makes CDMA technology for cell phones. It's interesting. So Viterbi is probably better known academically than Irwin Jacobs, who founded Qualcomm. But in San Diego, and I think in the business world, Irwin Jacobs is much better known. Andrew Viterbi has always been the vice chairman, and Irwin Jacobs has always been the chairman and CEO. But it's Viterbi who has an algorithm named after him. Both of them were actually professors at UCSD for a long time.
I have a question.
Yeah.
So conditional random theater considers yi depends on yi minus 1. Also consider the dependency of yi minus 1 on yi.
Yes.
How does this affect the user algorithm?
All that this algorithm is really doing is saying that we need to consider each pair yi minus 1 yi. And then for each pair, you get a sum of contributions from all the feature functions. And that sum of contributions can be positive or negative. But when we're doing the maximization, we're looking for the biggest positive here and the biggest positive here. But this algorithm is a non-probabilistic algorithm. It's just doing the numerical calculation efficiently, and then it's up to us to interpret this argmax as providing the highest probability label sequence y, and it's up to us to interpret a positive value for the G2 function as meaning that there's a positive compatibility somehow. I don't think that there's a lot of intuitive meaning to the algorithm. It's essentially an algorithmic trick. But there's a lot of intuitive meaning to wanting to solve the argmax problem because that gives you the highest probability solution. And then I suppose to make the argmax tractable, then there are two restrictions. One is that it's a linear function that you're looking for the maximum of. And then the second restriction is that you're only looking at these adjacent pairs of yi's. Okay. If there aren't more questions on this, I'll move on to the next algorithmic subproblem. Mm-hmm.